Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to talk about continuity at a point. So what I've done is I've given us a graph, and I really just want to know, where honestly, where's this discontinuous is the most important part. So I'm really just going to kind of look at interior points first, like the points, just the integer values 1, 2, and 3. And I want to know, is the function continuous at 1? Is the function continuous at 2? Is the function continuous at 3? So in calculus 1 so far, we've studied limits, and then we've also discussed how they compare to, the evaluation of the function. So really kind of in layman's terms, if I want to ask if it's continuous, well, a function's continuous as long as I can draw it without lifting my marker. So let's say I have a function over here. I can see that this function I just drew was continuous because I was able to draw it without lifting my marker, as opposed to something that looks like this. That function is not continuous at, well, let's just say at the C value here. It's not continuous at C because I had to pick up my marker and then move it down here to finish the drawing of it. But it was continuous, it was continuous from minus infinity to C. It was also continuous from C to infinity. But at C, it's not continuous. So it's kind of clear that we can see that, if I'm looking at these segments, it's continuous from 0 to 1, let's say open 0, open 1 right now. And also continuous from 1 to 2, from 2 to 3, from 3 to 4. Really what I want to do is I just want to investigate these interior points first, and then we'll talk about continuous at the endpoint second. Okay, so let's just kind of ask ourselves, when, for what values is this continuous? Is this continuous at 1? Well, I can see when I'm drawing this thing. If I'm going here, I'm going to have to lift my marker. Boom. Okay, so this thing's not continuous at 1 because in order to go from, from the interval from 0 to 1 to the interval 1 to 2, I'm going to have to lift my marker at 1 to continue drawing. Is it continuous at 2? Okay, so I drew it down here. I have to lift it to draw this down here, and I have to lift it to put it back. How about at 3? Well, it's continuous because I can go, all the way through 3 without lifting my marker. So, I always ask, well, what does that mean? Like, how would I tell, using what we learned in calculus, what would tell me that it's not continuous at 1? What would also tell me that it's not continuous at 2? Well, the first thing we can see is, it's not continuous at 1 because the limit doesn't exist at 1. I can tell that the limit from the left is going to go to 2, so the limit as x approaches 1 from the left-hand side of this f of x is equal to 2, and then the limit as x approaches 1 from the right-hand side of this f of x, well, as I approach from the right, we can see it's going to 3. So it's not continuous. I'm going to have to lift to go from, y equals 2 to y equals 3, essentially. Now, that wasn't enough because I can still tell that this function is not continuous at 2, so we can see that the limit as x approaches 2 from the negative of f of x is equal to, well, as I approach 2, this is going to go to this 2y value, and as I approach 2 from the right-hand side as well, so the limit as x approaches 2 from the positive side of f of x is also 2. So we can see that the limit does exist, but I guess that's not enough. If the limit doesn't exist, it's immediately discontinuous. But just because the limit does exist doesn't guarantee continuous. So there's an extra piece that we're missing here. Well, let's look at this. I know that this thing is continuous because I can draw it, through 3 without lifting my marker. So let's look at the limit. Well, the limit as x approaches 3 from the negative side of f of x, well, as I'm approaching from this way, it's going to be that 2. And then the limit as x approaches 3 from the right-hand side of f of x is, as I approach from the right-hand side, I can see that this is also 2. So I can see that the limits exist. Furthermore, I can see if I plugged in x equals 3, if I evaluate this function at 3, this is also equal to. So that looks like this is kind of the um, this must be it then. So notice that this thing's like for 2, we had the same thing that we didn't have the same thing. The limit exists. The function also existed. F of 2, also existed. It's right here. This is equal to 1. Unfortunately, the limit and the evaluation weren't the same. So it looks like in order to be continuous, the limit has to exist, the evaluation has to exist, and they have to be the same values. So that's the actual definition of this. So let's write the definition, and then we're going to put this into practice. So here's the theorem. A function is continuous at x equals c if and only if the 3 conditions are satisfied. So f of c has to exist. The limit as x approaches c of f of x has to exist. And furthermore, the evaluation and the limit have to be equal to the same thing. And we saw that in our previous example, that the only time it was continuous is if they went to the same spot from both directions, so the limit existed. The function was defined at that point, so that existed. And furthermore, the limit and the evaluation were at the exact same spot. So here's an example. I want to determine the value of, let's say c, for which the function is continuous. So let's do that. So our function is f of x is equal to say x squared minus 81 all over x minus 9. And this is when x is not equal to 9. And then at 9, let's call this, say, I don't want to call this c. Let's call this the value a. So, and then this is going to be equal to a when x is equal to 9. All right. So, in order to make this work, we have to really just go through these 3 conditions. And I'm really trying to find the value of a for which this function is continuous. So we have a piecewise function here, and we'll draw kind of a picture over here to make sure this makes sense when we're done doing this algebraically. So let's just kind of go through the steps. Number 1, we know that the function has to exist at that c value. Now, in this case, the spot that it's not going to be continuous is going to be at this 9 value because, for instance, this function here would be continuous everywhere except where the denominator is equal to 0. That's why I'm not allowed to plug in 9 here. So, and this function is equal to a when I plug in x is equal to 9. So the only spot where we have a problem of continuity is at this 9 value. So that's going to be our c value. So we have to make sure that f of c exists or f of 9 exists. Well, f of 9 is going to be, well, when you're equal to 9, the output is equal to a. So f of 9 is a. So therefore, it exists. Let's make this look like a 9 as opposed to an a. So f of 9 is equal to a. All right, 2. I know that the limit has to exist. So I know the limit as x approaches 9 of f of x has to exist. So, well, when I ask students, like, what does the limit care about? Does it care about at the point or very close to the point? So, what we know is the limit is not the evaluation, it's what happens when, you get extremely close to the point. So, what inputs am I using? When I'm trying to get close to 9, let's say, just kind of close, let's say 8.6 or something like that. So if I'm going to plug in 8.6, which is kind of getting gradually closer to 9 or 8.7 or 8.8 or 8.9, 8.99, and so on, we can see when I'm starting to get close to 9, I'm not actually equal to 9. So I'm using this function. So the limit of x approaches 9 of f of x is going to be the limit as x approaches 9 of this function. So this is going to be x squared minus 81 all over x minus 9. And I know I can't plug in 9 right now because it's not defined there. So I'm going to simplify by factoring. So this is the limit as x approaches 9 of x plus 9 times x minus 9 all over x minus 9. And I can see that this factor cancels, so your x minus 9 goes away. Should have been that one. I'll make this one the minus and this one the plus. So I'll have to erase. So this is the minus, this will be the plus. So the x minus 9s will cancel, so I'm just left with x plus 9. Now this function is, defined at 9, which means I can just evaluate it. So this will be equal to 9 plus 9, which is going to be equal to 18. So let's write that. So I know that the limit as x approaches 9 of f of x, so the limit as x approaches 9 of f of x is going to equal 9 plus 9, which is going to be equal to 18. Now here comes the very last step. So, boom, we got this one, we got this one. Now I have to figure out that one. Well, the limit as x approaches 9 of f of x better be equal to f of 9. So the limit as x approaches 9 of f of x better be equal to f of 9. And what I know is the limit as x approaches 9. Sorry, I'll do it this way. So the limit as x approaches 9 of f of x is equal to 18. So this side, I'll put it down here. In case we can't see it, I'll write it over here. So that's equal to 18. And f of 9, we did it up here, is equal to a. So this is equal to a. And we just found the a value that'll make this thing continuous. All right, let's look at this graphically. What did we actually do here? So if I was to graph this x squared minus 81, the quantity x squared minus 81 over the quantity x minus 9, well, I can see that this thing will simplify to just x plus 9, which is equal to a line, except this is not defined at 9. I know this one is, but what we did is we closed a hole here. So I'm going to draw x plus 9, or at least something close to it. So x plus 9 would be something like this. Now, remember that this is not exactly the same thing as this. They differ at 9. This is undefined at 9. So, at that C value of 9, we know that this is going to be an open circle. So it's going to be there. So for me to make this function continuous at 9, I really have to fill in what's called this removable discontinuity. It's a removable discontinuity because what it looks like is I just grabbed a point and removed it. So I need to figure out, does dot have to be? I have to fill in this point. Well, I know that its x value is 9. The question is, what is its y value? So what point do I have to plug in there in order to make this thing continuous? Well, we just figured out if this a was equal to 18. So if I did the points 9 comma 18, that's all that represents is the point 9 comma 18, then I've just filled in this hole, and now this function can be drawn without lifting my. So that is the value of a that makes this thing continuous. All right, let's do one more example. So this will be our last example. It says determine the value of b for which the function is continuous. So our function is another piecewise function, and I can see that it has, two pieces, 3x minus 4 when x is less than 2, or less than or equal to 2, and then bx plus 6 when x is greater than 2. So remember, we have to just go through our steps. F of that c has to exist. Now, for f to c to exist, we have to figure out, what is that c value going to be in this particular case? So we can see that, this is going to be a line that's going to be defined everywhere, well, less than or equal to 2. So this thing is continuous. It's going to be some line 3x minus 4 all the way till I get to, this value of 2. And this is also going to be a line. I don't know what its slope is. Our job really is to find that slope. And the other line is going to be another, a solid line. Who knows what it looks like? It could be positive. It could be negative. Let's say it looks like this, for instance. If that was the case, then, this is clearly not continuous. So my goal really is to make this slope work so that, it intersects this particular point. But again, the point of contention, or the point that we're worried about, is going to be at this 2. So I need to make this thing, continuous at 2. All right, so in order to do that, again, we just have to, step 1, step 2, step 3. So f of 2 has to exist. That's our first step. F of 2 must exist. So what is f of 2? Well, f of 2, when I plug this in here, I have to figure out, well, what function do I use when x is equal to 2? So, well, when x is equal to 2, I'm going to use this top function. So that means this is going to be equal to 3 times 2 minus 4. So 6 minus 4 is going to be equal to 2. Now, the second step says, well, its limit has to exist. So the limit as x approaches 2 of f of x has to exist. I remember that. So what does it mean for the limit as x approaches 2 of f of x exists? Well, we know that this is a piecewise function. I kind of drew it already, that I have, like, say, 3x minus 4, and this is going to be, at 2. It's going to look like some kind of line. And this is going to be another line. I'm just going to draw a little differently because who knows what its slope looks like. We have something like that. So if this was that piecewise function, we could tell that this limit would not exist. So what would make this piecewise function exist? Well, for it to exist, the limit from the left has to equal the limit from the right. So that's what we're going to do. That means the limit as x approaches 2 from the left-hand side of f of x has to equal the limit as x approaches 2 from the right-hand side of f of x. So our job is to figure out what f of x's go here for these particular limits, and it depends on on the domain restriction. For here, if I'm approaching 2 from the negative side and I'm approaching here, what I know is that this is going to be below 2. So, this x approaches 2 from the negative side means that I am in that interval, which means I'm going to have to use this 3x minus 4. So this f of x is going to be equal to 3x minus 4. So this is going to be the limit as x approaches 2 from the negative side of that. And over here, this is going to be the limit as x approaches 2 from the positive side of what? Well, if I'm approaching from the positive direction, I'm doing that, which means now I am greater than 2, which means I'm going to have to use this bx plus 6. So this is going to be equal to bx plus 6. All right. Now, both of these things are lines, which means you can evaluate them at x is equal to 2. So that's what we're going to do. We'll plug in 2. So 3 times 2 minus 4 is going to be equal to b times 2 plus 6. Now, 6 minus 4 is equal to 2, and this is equal to 2b plus 6. So subtracting 6 minus 4 is equal to 2b. So finally, b is equal to negative 2. So let's write that over here just to make sure. B is equal to negative 2, which was really our goal. I know there was a step 3. Step 3 says that the limit as x approaches 2 of f of x better be equal to f of 2. And if you do that, you can tell that its limit's going to be, one of these two sides. And then f of 2 is going to be equal to 2. So what you're going to do is just give, it's just going to give this equation back. So it's just going to give you the exact same b value. So regardless, this is going to be b is equal to negative 2. So you'll simply just solve it twice. So once you're done finding your B, you know that you are done. So if you like the content, thanks for sticking around, and please consider liking, subscribing, and sharing. Thank you.